So a very good morning to all of you. Today we'll start with a new topic which is known as testability measures, right? So like this diagram we initially discussed. Okay, this we'll see how it gets modified further. So the first thing is you have a problem statement, and from the problem statement and code is written, and then a netlist is prepared, right? And then you do some kind of logic verification. Okay, so that and once the logic verification is done, we know, okay, this is functionally okay. Then comes the fault simulation aspect. So there could be faults at various nodes. So all those things will be compiled, and then we do some optimization of the faults. That many of the faults can in a single test vector, many faults can be detected. So that is known as a technique is known as collapsing the faults, which we have again we saw that fault dominance and things like that we studied, right? Collapsing of the faults, right? Fault equivalence and fault dominance. So now you have an compressed small list of faults, and then you also from the netlist and the formal verification, from the logic verification, we have a set of test vectors which we can use. So all these inputs is given to the fault simulator. Now the final fault statistics coming out from the fault simulator should be for say fault A, B, C, D, E test vectors, and these are the T1, T2, T3 test vectors. Okay, and it could also come out that for a test vector T1 and a fault in a A, G, F, those simultaneously 3 or 4 faults will get detected. So that kind of statistics is available, and that this whole scheme is known as automatic test pattern generation, because manually we are not doing anything. So we have some algorithms which would run based on these inputs and give us the fault statistics. Okay, so and that would be known as automatic test pattern generation. So
कौन क्या है? पहले यहाँ थी ना? नहीं, पहले यहाँ थी. अब has reached on
okay, so now the thing is here when we give the test vectors from here to here, generally it is we have an it is the experience says it is better to have an random test patterns. Okay, so that at the least possible time we generate as many faults as, rather than going sequentially from 001 001. So randomly if you do that, the possibility of the test vectors being successful in capturing the faults will be much higher. So this is the but ultimately there will be few faults which are difficult to detect. So you will have to keep running the test random vectors for a long time to find, okay, to cover the 100% faults. Okay, so what we do is initially suppose we have a fault. Right, and the total fault list is available. We need to classify this into two groups. Okay, one is easy faults and one are difficult faults. And for the easy faults, now we run this random test and pattern generation. And for the difficult faults, what we do is we go for that. We pick up that specific fault. Okay, they could be 10, 20, 30, whatever those difficult faults. So and then the only option available there will be to do that sensitization, propagation, justification. So if you do this, definitely every fault will be a test vector which can detect this fault can be. So this process is a lengthy process, right? So that is the reason only for the difficult faults we go for this particular process. Okay, for the other things we are going to run few algorithms. So those algorithms also we would learn from the next class. Okay, so now after this class there will be an introduction to automatic test pattern generation. Followed by that there will be one class on on combinational ATGP automatic test pattern generation, and then followed by the sequential, for the sequential circuits, how to do that. Okay, so now the starting point is this, right? How to say, okay, these faults are difficult and these are easy. That is what we are going to learn in this particular class. Again, some manually we won't do that. There has to be some algorithm for the entire fault list. It has to make two lists, right? It has to classify the entire fault list into two lists. Okay, so how that can be done? So that is what we are going to learn now. Okay, so this is a setting difficulty level. Okay, one simple way of doing it. A simple way, it appears simple here, but algorithm wise and computation wise it is heavy, and that's why this is not used. Suppose what is the combinational controllability? Controllability means how to control a 1 here. Okay, so why do you want a 1 here? To detect a fault of stuck at 0. Right, so can I say the difficulty is 1 by 8? 1 by 8 means there are 3 inputs out here, and out of which only 111 will put a 1 here, all other things will put a 0. So 1 by 8 is the combinational controllability. Okay, now can anybody tell me a lower value of this or a higher value of this will indicate difficulty level, high difficulty level?
Lower value will
Yes.
show higher difficulty.
Okay, the high difficulty. So I can put this as well. So the combinational difficulty at this level will be 1 by 4 because there are 2 inputs out here, right? And to get a 1 out here, this also has to be 1, this also has to be 1, right? So you multiply these two. So it will become 1 by 32, right? So now, but that alone is not good enough, okay? Because now if I have to detect a stuck at 0 here, okay, what is that I need to do? I need to put a 1 here, right? And also I need to enable this gate, right? So that this is seen out here. So I need to put a 1 here, isn't it? If I put a 0 here, then it won't help, right? I have to detect a stuck at. I have to detect a stuck at 0 here, so I'm going to put a 1 here, right? But output I have to see. Okay, if I am giving 1, I should see 1, right? If I am seeing a 0, that means it is stuck at fault. But for this to happen, okay, this gate needs to be transparent, so I need to put 1 here. So for a stuck at 0 fault, okay, so the difficulty level is making it this point 1, which is on 1 by 32, and also making this point also 1, right? Right, only then this. So I have to multiply by 1 by 4 out here. So so this is why this is one method of doing it. For a small circuits you could do this where there is not very large number of gates. So this is one method of doing it. So it will say, so for each of these nodes. So now similarly you can find a difficulty level to detect stuck at 1 there, right? For example, if I take this node to find what is the difficulty level to find stuck at 1 here, right? So to find a stuck at 1, I have a 1 here. For that it is 1 by 32, and I need to put a 0 here, right? And to put a 0 here, it is slightly easier than putting a 1 here, because out of the total 4 vectors which is available as input, 3 vectors can generate 0, so it will be 3 by 4. So 1 by 32 into 3 by 4, right? So such each faults, all the faults a algorithm can run, and at each node, for each fault associated with each fault, it can find the difficulty level of combinational controllability 1 and combinational controllability 0, right? So combination controllability 0 indicates, right, at this point, right, it is just on a partial thing, right? Now for as far as the difficulty level, to find the difficulty level at this node, now for stuck at 0, for stuck at 1, CCO into CC1 of this. Okay, so for having done these CCO1 and CCO0 at each nodes, then you go one step ahead and compute accordingly the stuck at fault. So this is, since it is an if it is an OR gate, then I would want a 0 here, right? So that depends also kind of on the kind of gates, because if in an OR gate, when I have to pass the information from the top input, then the bottom input has to be 0. Okay, if I put a 1 here, then it get masked. Okay, you have a permanent 1 outside. So depending on the gates also. So this is one way of doing it. It can't be done for very big VLSI circuits. For small circuits, we can do this. Okay, so this is one way. Now we have something known as a better option, which is known as Sandia Controllability, Observability Analysis and Program. Okay, SCOAP, Controllability. And now it has got several numerical measures. One is combinational 0 controllability, a combinational 1 controllability. This is same like what we saw here. CCO0 and CCO1 is the same. It also has an additional measure, which is known as a combinational observability, which is known as CO, right? So this is same for 0 and 1. Okay, so there is no distinction between 0 and 1. And then similarly, it has got for sequential circuits also. So this sequential circuit aspect we will learn after having covered the sequential circuit. So as of now, we have not touched upon sequential circuits at all. So we'll come back to this testability measures after sequential circuits to cover this aspect also. How to go about defining the difficulty level is, so the first step is for each primary input. Okay, if I have to put a 0 at the primary input, it will be known as CCO0, and we say the difficulty level is 1. Okay, this is just to start with. Okay, 1. You can start with a 0 also, it doesn't matter, right? But whatever he has proposed, we will go as per that. It doesn't make any difference. You start from 0, -1, 2, but some reference. Okay, so it is assumed that to put a value 0 into the input, okay, the difficulty level is 1. Okay, and then similarly, the difficulty of controlling each primary input to 1 is known as CC1. And that is also 1. That means the difficulty level in putting a 1 into any of the primary inputs is also 1. Okay, so this 1 value we give initially. Then we move forward into the circuit. Okay, once we move forward in the circuit, okay, now like two things have to be done. Okay, one is when you move from the input of a gate, okay, to the output, you difficulty level, you add 1. Okay, so irrespective of what kind of gate, okay, whether it is 2 input gate, 3 input gate, OR gate, AND gate, NAND gate, okay, it doesn't matter. Okay, whatever it is, irrespective of the gate, I add +1. Okay, now the other thing, okay, here the controllability, okay, it is defined by these two equations. Now what are these two equations? If a logic gate output is produced by setting only one input to the controlling value, then it is minimum input control, minimum of the input controllabilities. Like suppose I have 2 inputs, the controllability of putting say 1 out here is X, and putting a 1 out here is say for an AND gate, for example, the minimum effort required to put an 0 out here, okay, X is X, and the minimum effort required to put 0 at this node is Y, but to put an output 0, right, both of them need not be put to 0, only one of them can be put to 0, right? So in such conditions, okay, that is in a logic output is produced by setting only one input, only one of them is required. In that case, you can take minimum of these two values. Okay, so this is minimum of those two values. But in case both these inputs needs to be set to some value to get an output, like for example, if I have a NAND for to get a 1 out here, I need to put a 1 here and 1 here. So this will be a 1 plus 1. Okay, output will be 2 plus 1 for the gate. So the total difficulty level out at the outside will be 3. Okay, so this is just one part of it. We have to move from the input towards the output applying this logic. Okay, so let me explain you for each gates. Okay, now for this AND gate, can you tell me what would be the controllability of 0 at the output?
2.
Yeah, 2. Okay, so that is I need to put only one of them 0, right, plus 1. Okay, now I will talk in a general term. We will talk as CCO A plus CCO B, right, plus 1. Okay, why I am talking this is as we move forward in the circuit, let me show here. As we move here, it is not 0 or 1, right? Because here already it has been computed, right? So for this particular gate, the inputs are not primary inputs. Okay, so in that way, so let's take it in a generalized manner. So for to get a 0 out here, it will be a minimum of this and minimum of this of zeros plus 1. Okay, whereas for the 1, it will be because both have to be 1, so 1 plus 1 plus CC1A plus CC1B plus 1. Okay, is this thing okay with all of you? If you have a doubts, please ask, because unless we understand these basic things, and forward it will be difficult. Is it okay? Yeah. Okay.
Yes, sir.
Okay, thanks. So for an OR gate, similarly, right, if I have to have a 0 at the output, right, I need to have this also 0, this also 0. Okay, only then I get a 0. So I need to add the combinational controllability 0A, combinational controllability 0B, and then add 1. Okay, so this 1 comes because we are moving from one gate to other. So irrespective of the type of gates, this plus 1 will be there as we are moving forward. Okay, whereas for 1 out here, if you put 1 anywhere, you will get a 1. So it will be a minimum of these two. So you put 1 there. Similarly, for an XOR gate, so you could see that, right? If I want an 1 out here, right? So it could no. If I want a 0 here, this is a 0 plus 0 or 1 plus 1, right? These are the two. So I need to do CCO 0 plus CCO 0A plus CCO 0B. Okay, a minimum of that, or CCO 1 CC1 plus CC. So these are the two combinations, right, possible, right, for 1. But among them, whatever is minimum, right, because these inputs are coming from different gates. Okay, don't think it as a primary inputs. Okay, it might be coming from different gates. So it may be so possible in a circuit that CCO 0 plus CCO CCO A plus CCO B is lesser than CC1 plus CC1 B. So you might want to take this. Okay, so you have to take a minimum, because both these conditions is going to push a 0 outside. Right. Similarly, this also for a 1, 1 is 0, 1 is 1. Now the inputs have to be complementary to each other. So these are the two possible combinations. Among these two possible combinations, whichever is the minimum, you take that and plus 1. Right. So for the NAND gate, again. So for
Sir,
yeah, tell me.
Sir, for XOR gate, as we discussed, like for example, for OR gate, CC0 condition score will be 3, and for CC1 condition score will be 2.
Yes.
So in case of XOR gate, if we consider like CC0 condition, so in minimum and in bracket, then we have like 2 conditions.
Yes.
So if one of that is fulfilling, then it will be like 1 plus 1 and then additional 1 for gate.
No, this is 1 plus 1 plus gate. If the
total 3 should be there.
Yeah, 1 plus 1 total, it will be 3. In case they are primary inputs.
Okay.
Right? In case they are primary inputs. Right? They may not be like we are taking that CC01 is 0, right? It may not be 0 always. It will be 0. No, it is. It may. We are taking it. You are assuming it to be 1, right? So it may not be 1 always, right? I gave you an example, right? So that is only for the basic gates. Like for this example, let me show. Here you see the value is here is different, right? For this gate, CC0 and CC1 inputs for this gate is different, right? So this is a generalized expression.
Okay.
Right. Okay. Similarly, for a NAND gate, I will find for to have a 0, right? So both of them have to be 1 here. So I put an plus 1. So if I take it as a primary inputs, then the score will be 3, right? But if I take these as if I want an 1 out here, one of them can be 0. So I take minimum. So minimum means right 1 plus 1 2. Okay, so okay, if you want to consider, just for clarification purpose, if you want to consider this as primary input where the score is 1, right? So in that case, this will be 3 and this will be 2. Okay, out here the score will be 2 and 3, right? Similarly for a NOR gate, okay, so 1 1 will give a 0. So that is the or 0 1 or 1. So a minimum. So one of them needs to be a 1 and then it will produce a 0. So minimum of CCA1 and CCA1. So this total score will come out to be 2. Whereas to have an 1 out here, both of them have to be 0. So you add these both. So this score comes out to be 3. Right. Similarly, this is for XOR and a NOT. So is this table clear to all of you? Right?
Yes, sir.
Okay, so let's move forward. Right now, after doing that, now we start the reverse also from the primary inputs. Okay, so this is a kind of one way we go ahead, trying to because a fault needs to be propagated, and then finally we need to bring back the fault to the primary inputs to define the test pattern also, right? So this analysis, it does a reverse path also, which is known as observability. In the reverse path, the primary inputs, irrespective of what is to be observed at primary output 0 or 1, we start with a level 0. Okay, now you might be wondering why we are not starting with 1. You can start with 1 also. So if you start with 1 also, it will give the same kind of, finally we are going to find an on a relative scale, okay, what is difficult and what is more. Okay, but anyway, when this algorithm was made, it was decided that okay, primary input is just measuring some value. Okay, so the difficult, it is just you are observing something, so you need not start with an just for observing, you need not even put any difficulty level. Whereas in the primary input, you are doing some effort to put some quantity there, 1 or 0, right? So this is just observing a value, so that's why it was taken as a 0. Okay, so we will stick to this philosophy of 0 rather than going for a 1. Okay, so because that has been defined like that, so we'll stick to this. Okay, so 0, and then we move back. So again, when we are moving back, we add an 1 to the logic depth, right? And also for to observe this particular output, right? Now, what is the like, for example, suppose I have I put this is 0 here. When I move here, right? So I need to add. So this gate needs to be made transparent, right? Only then this will be seen here. So when I move back, so what is the controllability? Okay, of 1 at this node, that will be added, right? So it will be 0 plus 1 plus CC1 of this particular node when I am moving backward. Is this okay? Now if I give another example of an OR gate, right? If I am moving from here to here, say I start with 0, right? Because this is one gate, I take 1 here, right? And for this to be for this observability aspect, right, I need to, like we did the for the fault and propagation justification aspect, right, similar thing, I need to put a 0 here, right. So this for this observability I need to put an CC 0 here at this particular point. Okay, so this is how for this gate I move backwards. Now if I see here for an AND gate, this is the observability at the output, right. Now coming to the observability at the inputs, okay, this at both the inputs the observability will be, right, for this 0, right. So there is no 0 and 1. It does observability doesn't distinguish between 0 and 1, because if I am setting 1 here, A and 1 both will get transmitted from here to here, right. So I just this final value, okay, is CO. Okay, this is not CO1 or CO0. It is it is just observability calculation. Okay, so CO. So at A, it is 0 out here, plus 1 gate. Okay, this is 1 gate, plus CC1 at B. So CC1 at B. So can somebody just prompt for this particular gate, and then we move forward. What would be at A? A similar equation for A, if you could tell me.
It's C0 A equal to C0 Z.
Yes.
Plus CC0 B,
yes,
plus 1.
Yeah. Okay. So it is like this, right? And this is going to be. So this way for this gate also, right? Now for this gate, probably you can have a look. Now suppose this is the output, and I am bringing out here, right? So so for this gate to be transparent, right? So at A, it is either CC B is if it is 0, right? If it is 0, then what happens? This can come here, right?
Yes.
Right? It will be whatever is Z here, same Z I will get. If it is 1 here, what happens?
It will be also 1. A will be also 1.
No. If it is 1 here, suppose this is Z, this is 1, then what will be here?
Z bar.
Yeah, it is Z bar.
Z bar, yes.
Right? So it means that if I have a 0 or 1, right, this will get transferred here. Doesn't matter. Correct? That inversion is permitted. It doesn't matter. Right? So that like for an inverter, the data is getting inverted. The only thing is it should not get permanently masked as 1 or a 0. Right? So for an XOR gate, right, CZ0 and a minimum of C0 0 or B, because you can put either values, it doesn't matter. Only thing is when the algorithm runs, and it will from here to here, it will consider it as an inverter. It doesn't matter. Suppose I talked about a D algorithm. We'll discuss that in detail later on. If it is a D here, it will come out as a D bar. If it is a D bar here, it will come as a D. Doesn't matter. Okay. So that is okay. So this is for an XOR gate. So you could expand these things for the other gates as well. Okay. So when you have branchings like this, right, then for many inputs outputs, if they are being driven, right, this can happen, right, in a gate. When I have a gate which is driving, right, from, then whatever is the minimum from whichever gate it is coming, okay, that needs to be taken, okay, from here to here, or here to here, or here to here, right. So whatever is the minimum that needs to be taken. Okay, I think there should be +1 also. It is amazing. You could verify that from the textbook. Okay, this from again our textbook only prescribed. So I think there needs to be +1, right? Okay. So now we take an example out here.
In that branch was not there, sir. So I think due to that, but gate is not there. Only branch.
Yeah. Okay. Thanks. Okay, because gate has not been mentioned out here, right? Suppose there are generally it would happen that all these are going to different gates. Yeah. Thanks, Jay. If there are several gates, then when we move here, whatever comes, okay, that the minimum will be there. Okay. Now let's try and analyze this particular circuit, right? Now I put the primary input difficulty levels as 1 1. Okay, 1 1. Primary this is for okay, this format is first 0 and then 1. Okay, controllability of 0 and 1, 0 and 1. So I write 1 1. So this is the standard format. Okay, the way it is written in the brackets. Okay, this stands for CC0 and this stands for CC1. So coming out of this AND gate, okay, for a 1 it will be 1 plus 1 plus 1 3, right? So this is also 1, this is 1 1. So for a 1 it will be 1 plus 1 plus 1 for the gate 3, and for a 0 one of them needs to be 0. So 2 3 is this this input output which we have written is clear to all of you?
How it came to, because 0 is not given at input.
No, the difficulty, no, this is the difficulty level, right? So the difficulty level of 0 is 1 1.
Okay.
Right.
Okay.
Right. So minimum of that 2.
Okay, sir.
So minimum is minimum of 1 and 1 is 2, 1 plus 1 level 1, because moving forward in the so this formula we have used, the top one. Okay. So for an inverter, okay, just it is a gate, so 1 level high, and what would be the output out here? Can anybody say? Here at the O. Simple, right?
3, 4.
3,4.
Why 3, 4?
3,5.
3,6, right?
Minimum.
First is for 0 it is minimum. Okay, 2 and 2 minimum is 2 plus 1 3, right? For 1 this plus this 3 plus 2 5 plus 1 for the level, so it will be 6. Okay.
Can you repeat this concept? How it came 6, sir?
For an AND, right, to have a 1 here, I should have 1 here and 1 here, right? So that difficulty level or controllability of CC1 is 3 here, CC1 is 2 here, so I should have both of them together. So 3 plus 2 plus we are moving from input to the output of a gate, so plus 1 here. So this, so 3 plus 2 plus 1, I am getting 6.
Yeah.
Right. So this is the thing, right? Now okay, now let's just do a small analysis. Is this making some sense, or it is just putting these values is actually making some sense? Now if you see here, now suppose I have to find a stuck at 1 fault here, right? Now what I need to do is I need to put either 0 or 0 here. Okay, so that is one condition. I can put a 0 here, 0 here. Okay, I have to find a stuck at 1 fault, right? So I have to put a 0 here. So one difficulty level I can say it is 0 0, right? So I can put I can pick any of these 3 vectors. So 1 difficulty level plus this should not be stuck at 1. Okay, right? No, when I'm putting 0 and 1 here, this should not be stuck at 1. Right, so that is an otherwise there is no point here. Similarly, if I am putting a 0, it should not be. So that is why this is coming out to be 2. Okay, there are 2 different set of conditions that needs to be satisfied, right? But when I have to do it 0 out here, right? Then okay, first I have to set an this, right? And also I have to set condition out here also, right? So it is becoming more difficult here. So that is the reason, and as you move, if you logically think, these value will actually boils down to the number of conditions which it has to meet. Now, if you talk about 6, if you try to analyze the kind of conditions required to put a 1 out here, it is fairly large number of conditions. If you see here, that means there has to be 1 here, there has to be a 1 here, there should not be a stuck at 0 here, there should not be stuck at 0 here. So many conditions would come here, whereas for 3, right, this is for to bring a 0 here, it is fairly easy. That means if you are going to bring a 0 here, irrespective of what is happening in y, still I can get a 0 here. So this is slightly easier. So if you see all this analysis, if you try to analyze it physically, okay, the kind of effort or difficulty level, it actually is a good algorithm you will find. Okay, so these things I have just written. You could go through it in the PDF. So this is just trying to physically tell, okay, that the difficulty level, actually these numbers they really fairly indicate the difficulty level. Okay, so there's okay. Now we have to do the reverse path also. So this is 0 out here, right? So what will be x and y for CCO? Anybody?
Two and 0.
2. Here will it be 2?
1 and 1.
No. See, for this 0, okay, to come here, right? First of all, this is 0. So I write a 0, right? Plus there is 1 gate, okay? So I put 1 here. And now what is this? How will this node be reflected here? Y should be put to 1. Correct? And how difficult is it to put y to 1? 2. Right? So can I write 3 out here? Is it okay?
Yes, sir.
Right? Okay. Now similarly here for this particular node, this is 0, right? So I write 0, plus I am coming back, so I write 1, right? And then what is the difficulty level in setting this node to 1? Because I have to set it 1 only, then this becomes transparent out here, right? So this is 1, so I write 3. So this total now becomes 0 plus 1 plus 3, it becomes 4 here. So I will write a 4 out here. Okay, so when I'm coming back here, this is just a single gate, so I just write 5 here, right? Here it is 1 1, right? So this 3, what will this 3 become here?
5.
Yeah, 5, right? 1 for the gate, and here it is an additional 1, so 5 and 5. Okay, so these are going to be, I hope that I have done it correct. Yes. Right. So these are the values which we get. Right. Now, once we do this, finally, okay, this all the three is simultaneously we don't analyze. Now we say to check as stuck at 1 difficulty at this level. Okay, what is the difficulty level? So to check stuck at 1, okay, what is the to detect a stuck at 1, I need to put a 0 here. So what is the difficult controllability of to bring 0 out here is 2, right? Plus the observability aspect. So for an at this particular node, if I say the difficulty level of stuck at 0 is 5, and to detect a stuck at 1, the difficulty level is 6. Is this very clear to all of you? first we do this analysis, and subsequently, okay, final thing is what is the total difficulty level of stuck at 0 here and stuck at 1 here. So these two figures, right, you add up these, right? This is an for a stuck at 0. Now you have to no, sorry, I made a mistake here, right? For stuck at 1, right, I need to put a 0 here, right? So which is 2 plus in the reverse path it is 3, and for stuck at 0 I need to put a 1 here, so it will be 3 plus 3, right? So this comes out to be 5 and this comes out to be 6. Is this okay with all of you till here? Kirti, understood? Jay?
Yes, sir.
Okay.
Sir, output when we are going on the reverse path, like if we are checking for node X, that 0 to be there, why can be 0 or 1 also? Why only 1 we have to?
Because if it is a 0 here, right, this is not going to be transparent, this gate. This will become, right, 0, permanently 0. Correct, Anjali?
Yes.
Right, it has to be 1 for this data to be propagated like this, right?
Okay.
Whereas for an OR gate it has to be 0, then it will get propagated, right? Because in an OR gate, if I put 1 there, then the output would be like permanently 1. So you want this data to be moved from here to here. Right?
Okay.
That is possible only when I put 1. Okay. Now, similarly, for this particular node, if I see here, it is 0. This is 4 we already got. Now, if I have to, for a stuck at 1, right? For a stuck at 1, I take this 2 plus 4, 6. Right? So it is more difficult. Now, let me just whether the entire thing is making sense. Now it is saying for a stuck at 1 here, okay, the difficulty level is 5. For a stuck at 1 here, the difficulty level is 6. Okay, but if you see this circuit also, you can straight away say, obviously, to detect a stuck at 1 at this particular node, okay, you need to make this 1, and to make this one there are 2 inputs, so effort required is greater, right? Whereas the other way around, if you have to find a fault of stuck at 1 here, okay, to make a 0 here is pretty important, easy, because this is an AND gate and this is an inverter only. So obviously, so between this and this, you find this is slightly more difficult. So if you do this analysis, so if you just do only the from input to output, you won't get a fair idea. But if you consider both of them and you take this total like this, it is pretty accurate, and it is an actual measure of difficulty level in doing and fault. So first, when we have the fault list, so we will the algorithm will run this analysis, and then you can say, okay, finally all those faults which has got a difficulty level above certain threshold value, say whatever 50, 60 in a big circuit, okay, anything about 40, we will do an sensitization, the propagation and justification algorithm, and for the rest of them, let's do a random test pattern generation. So that analysis will be done. Okay, so so this is again a simple thing. You could score good marks in the exam also if certain questions is given. Now let's take this example, and let's discuss this threadbare, and because if this circuit is clear, I think you will be good for exam. Any kind of questions you will be able to answer. So this is a 1-1 in the primary. It is 1-1 here also in primary. So let's take the top path. It is a 1-1 here. Now this has got an additional input. Okay, so this is also a 1-1, and it has got again a third input which is coming here. So let's first for this to move forward here, we need to compute the third input. So we come in the bottom, right? So from 1 1 I reach to 2 2 because this is an inverter. Okay, and this is 1 1, again I reach to 2 2 because this is an inverter, and this is an AND gate, right? So AND gate is for 0 minimum of this, so 2 plus 2 2 and 2 minimum is 2 plus 1 gate, so this is 3, and for 1 it is an 2 plus 2 plus 1, so this is 5, so this 3 5 is coming here. Okay, so how are these three things coming here in the output? Is it okay with all of you till here? Is it understood? Yeah. Okay. Now this is a NOR gate. Okay. Now for an NOR gate, right? Now if you see for an 0, to get an 0 out here, if anything is 1 here, it will go 0, right? So any one has to be 1. That's the condition for a NOR gate, right? Any thing is 1. So so it says a minimum of all these three. So 1 1 and 3, the minimum is 1 plus 1 for the gate. So this becomes 2. Is it now clear how this 2 has come? Yeah. Okay. Now for this to be 1, all of them have to be 0. So I have 5. All simultaneously, all of them have to be 0. Okay, for a NOR gate. So 5 plus 1 6 plus 1 7 plus 1 gate.
Sir, this is it's consider 0 for 1 and 1 for 0, right? So
pardon? Yeah. Correct.
we will consider minimum of 1 1 and 5, right?
1 1 and 5. Okay, 1 1 and 5. And if I have to have a 1 out here, all of them have to be 0. So 3 plus 4, 3 plus 1 4 plus 1 5 plus 1 for the gate 6. Okay. In the how did we get this 2 is minimum between 5 1 1 1 1. Okay. Thank you. So that is how we get 2 and 6 out here, right? Now I can I have an 2 and 6 out here. Similarly, if I do this analysis and 2 and 7 here, so this 3 and 5 is straight away available here. For this AND gate, if you see here, this is 3 and 5 available here, 1 and 1. So 5 plus 1, then this becomes 7, right? Minimum of 3 and 1 is 1 plus 1 for the gate, so 2 7, right? Now if you do, this is an OR gate, right? For a 1, it is a minimum of 2 and 2. Plus 1 for the is there a mistake out here?
Gate 1 for gate 2 0 2 3 should be there.
Minimum of 6 and 7 plus
6 and 7.
So for 0, I think it's right.
Yeah. For 0, both of them
2
have
plus
to be
2 plus
0.
1.
2 plus 2 plus 1, right? And for 1, it is minimum of 6 and 7, which is 6 plus 1 7.
Plus 1.
Okay. So I keep getting confused. Okay. Now okay. Now so all that is done. Now you have to go backward also, right? For backward, I put in 0 everywhere, right? And then I keep going back. Right now, if you see here, this is now let's take this particular condition where it is in a 0 here, right? This is an OR gate. So if I have to move it here, this has to be 0, right? For an OR gate. So 0 plus 1, and what is the thing for 0 here? 2. So this comes out to be 3 here, right? And for this particular net, again, this is 2 here to get a 0 here. So 0 plus 2 plus 1 for the gate, so 3. So this 3 and 3 I write here. Is this okay with all of you till here? And this is 0 is coming from here, 3 is coming from here. So this is a branch, right? So minimum of that we take 0 and 3. So I write a 0 out here. So these 3 values are okay. Then we move for. So this 0 again, this is a wire here. It comes out here, right? I hope it is okay till here. Now from moving from here to here, right? Now if you see 3 plus 1, right? And now right, for this to be transparent, both of them have to be 1 out here, right? So this also has to be 1 and this also has to be 1, only then this gate will become transparent. So it is 5 plus 1, right? This is a NOR, right? So there had if it is a 1, it will force a 0 here, so it has to be a 0 0. So for this, if you see here, this is 3 plus this one plus this one plus 1 for the gate, and I get 8 here. Is this okay with all of you? How did I get this 8?
Yes, sir.
Right? Okay.
Sir, can you please repeat? I didn't get.
Okay, sure. Right? Now I want to push this 3 here. Right? Now how will this gate become transparent? If I put a 1 here, what will happen? If I put a 1 or here, this will become 0, right? OR gate, this will become 1, this will become 0, right?
Yes.
So for this data to get reflected here, the desirable inputs will be 0 and 0 here, right? Then whatever this becomes, whatever we put value here will start getting reflected here. It will get inverted, but it will get reflected here, correct? If you put a 1 here,
yes,
this will get masked. So this is 3, right? Plus 1 for the gate, 3 plus 1, 4. And to get a 0 here, I have to put 3 plus 1, that is the difficult. 3 plus 1, right? 4. 4 plus 3, 7, plus 1 for the gate. So I put 8 here. Okay, Rahul?
Okay. Yeah, thank you, sir.
Okay. Similarly, now if I go for...
here also, is it like for simplicity, because that it is a 3 input NOR gate.
Yes.
So for simplicity's sake, we are putting both zeros, or
no.
Because 0, 1 also.
No. If it is an no, suppose I take an OR gate. If I put 1 here or a 1 here, the output will become 1, right? If this is 1 0 also, it will give me 1. Right? If I want this x, whatever x could be 0 or 1 to be reflected here, right? I have to put a 0 here and a 0 here.
NOR, no, sir.
For a NOR, I put a bubble out here, so this will become x bar. But this transparency condition remains the same. Is it okay? Okay, you are not convinced, so let me explain it once more. Right? Let's talk just about an OR gate. 3 input OR gate, right? If I have some input x, which could be 0 or 1, if I want to see at the output, okay, what should be these two terminals for an OR gate? 0. Right?
0.
Right? If I put 1 anywhere here, if I put any 1 here or 1 here, the output will become 1. So this x doesn't get reflected output, reflected at the output. So for me to see the output at x, I have to put 0 0 here, right? X. So when I talk about instead of an OR gate, if I talk about an NOR gate, I put a bubble here, but the condition remains same. Only thing is x will become x bar here, right? If I put 1 in any of these terminals, if I put 1 here, okay, this will become 0 here and this will become 1 out here, and x will not be visible at the output. Is it okay, Ranjani, now?
Okay, sir.
Right?
Okay.
So both these conditions have to be met, 0 and 0, and that is why we are doing 3 plus 1 plus 1 for the gate. So 3 plus 1, 4 plus 1 for the gate, and 3 was already there, and that is why the figure 8 came. Okay? Right? Is it okay?
Yes.
Yes. For now, coming for this particular thing, right? It is like 3 is there, okay, and 0 is here. It is just 1. 1 plus 1, 2 plus 1 for the gate plus 3 here, so it is just coming out to be 6. right? So now you understood, right? So all these things have to be, you have to work backwards, and you have to write this, right? Now this is just the run, and you are getting the data.
How is the middle one, sir? Middle one.
Middle one.
Middle one 8 is how? Yes, sir.
Yes. So it is 3 plus 1 gate 4 plus this 1 and plus this 3.
Okay.
Right? It has to be 0, 0. So that is coming out to be 8.
But sir, when we are talking about forward is, then we have taken first column as CC1 and second column as CC0.
No, CC0 and CC1. This is CC0.
Then how you got 2 or 6 for CC1?
For CC1, is it? To get a 0 here, right? Because there is an inverter out here, right? To get a 0 here, okay? What is that I need to do for an OR gate? For an OR gate.
Okay.
Right. So right. So this is a bubble out here. So that is why.
Okay.
Okay. So that is. So we do this analysis, and finally, okay. I have not. This is just the last step. Is to compute the difficulty level for an stuck at 0 here. Like, right, this is just, if I have to find a stuck at 0 difficulty level here, what will be the final value?
5.
5, right? Because I need to put a 1 here and this is 0 here, right? Now for a difficulty level of say stuck at 0 at this level, what is the value? 5, right? So you have to think now. Same thing at this particular level. For both it is 7, right? It may not be same thing for like for stuck at 1 out here. The difficulty level is only 3, right? 3 plus 0, right? So that is the final step, and the final step is not shown in this particular slide, but you need to know this is there in your textbook. But these things also you need to remember. Finally, in your exam you might want to you will be asked to give this particular value, so you need to remember that. Okay, so you can right, if somebody is interested, these are the some of the references which